LCMP, an automatic learning-based parameterized verification tool.
Think about a distributed memory multiprocessing system as shown. Two processors request to read data in memory in turn, then one of them replaces the data with 3 directly to its cache. Now, when the other processor read data from its cache, it will read 5 instead of 3, because the replacement action in cache 3 has no effect on cache 1. This problem is a cache coherence problem, and it should be prevented by finely designed protocols. Besides cache coherence problems, there are many other concurrent problems existing in many practical areas. Therefore, parameterized protocols are needed to prevent these problems from happening. After parameterized protocols are designed, how can we know whether they are correct? Because the parameter has no bound, to enumerate all of them is impossible. Therefore, it is necessary to verify it with more realistic solutions. To address this problem, many works have been proposed. They fall into 2 main categories: manual and automatic works. However, they have several drawbacks, which need to be improved. Therefore, we propose LCMP, an automatic learning-based parameterized verification tool. It combines machine learning and parameterized verification, which can learn directly from instances of protocols, and derive understandable auxiliary invariants. It can benefit protocols designers and researchers, providing them a deeper understanding of how the protocols are functioning. It also can give the direct result to business analysts who only need to know whether the protocol is correct or not. Now, we give an overview of LCMP. We can see that there are 2 phases in LCMP. The first phase is learning phase. It learns a set of auxiliary invariants from the input protocol. The second phase generally follows the idea of parameterized abstraction and guard strengthening technique, but in a more active way. LCMP executes strengthening process before abstraction, which avoids the occurrence of counterexamples and the guidance from humans. We have tested several typical protocols in LCMP. We can see that LCMP can even verify Flash protocol successfully. The experiment result can be found on GitHub. So, let's see a demo of how LCMP works. Before running LCMP, Murphy and Python 3 need to be installed properly. The installation is simple, so we will not go into details. Okay, let's start. First, let's see the help documentary. We can see that there are 3 categories of options, 8 specific options in total. Among them, protocol name is required, while other options have default values. Now, we try an example. Input the protocol name, German, and use default options except for the number of processes because we want it run faster. Then we can see LCMP calls Murphy to generate reachable set and transforms it into a dataset. The learning process is generating frequent set and learning association rules. Then LCMP carries out a series of action to select auxiliary invariants from association rules, with the help of Murphy. This process costs most of the time. Now we can see the first phase is finished, followed by the second phase. The strengthening and abstracting processes are executed rapidly, and the result is printed out. Finally, the generated protocol also needs to be subjected to Murphy, together with used auxiliary invariants. We can see that the newly generated protocol with all the used auxiliary invariants passed the model checking, which means German is verified successfully. Let's see what files are generated in the German folder. We can see that there are several important files are generated. Besides, if we have already run a protocol, then we can pass the option load to find out the answer quickly. That is the end of this demo. Thank you for watching it. If you have any question, please contact us by email. Goodbye.